Okay, we were talking about the Doppler effect. Okay, and that is not in violation of the thing we were talking about the other day about how the frequency of a wave never changes. Okay, this is a perceived change in the frequency. And because either the observer or the source, in our case just the source, is moving. Right? And what that does is it doesn't alter the waves, it alters how we encounter them. Right? And we talked about how in front of a moving object, you're going to hear what we call a blue shift. Okay? You're going to hear a higher frequency because as the train is moving forwards and hitting the whistle, that those waves are not going to get as far away from the front of the train before it produces the next one. That's going to make it feel to us like the wavelength is shorter and the frequency is higher. Behind the train, the opposite occurs. Okay? As the train makes a wave, it runs away from it before it produces the next one. All right? Making it seem like the wavelength is longer and the frequency is lower. Okay? And so you hear that altered frequency. I played the video of the fire truck, the British fire truck. Okay, going by, okay, and we could hear the wee-wah, okay, but we could hear how it changed, okay, before and after. Okay, I found another one. Okay, this one's with a person honking their horn. Okay, we hear that shift, right? Okay, we hear that shift of its high pitch as it's coming towards us. It's lower in frequency as it passes us and goes away as it retreats. Okay, but the frequency of the horn isn't any different than if it was one of you guys in the parking lot laying on your horn. I don't know why you do that. Okay, but you're stationary and it doesn't change the frequency of the sound unless I'm on supervision running towards your car because I'm annoyed by you. Okay, but it doesn't really because I can't move fast enough because I'm old. Okay, to create any Doppler shift in that. Remember that to have that Doppler shift, you do have to be moving at least some notable fraction of the speed of the waves themselves. Okay, yeah, you can turn that back up, please. Okay, that's why we don't experience a Doppler shift for light. We can't move fast enough to perceive a blue shift or a red shift because we can't move anywhere near as fast as light waves do. Right? Ringing a bell from yesterday. Okay. Reminders. Okay. Other reminders here. Okay. Unit 4 exam next Thursday, so a week from today. Okay. Make sure that you're ready for that. Final exam June 24th, 9 a.m. And the mock final options. Okay. Make sure you find one of those in your calendar that will work for you if you're wanting to do that. Obviously, you don't have to, it's optional, okay? But figure out which one of those is going to work for you, and then when I put that sign-up sheet on next Friday, okay, you can pick the one that works best for you, right? And also that June 13th at 12:20 deadline for any overdue assignments. Okay, you must have them by then if you would like to have them graded and added to your final mark before the final exam. Okay? All right. What was the other one I was going to show you? I don't remember. Okay. So, yesterday we worked on using a little bit of problem solving using the Doppler effect formula. Okay, so a reminder, the Doppler effect formula looks like this. Okay, F is the Doppler frequency. It's the frequency that you perceive or measure or hear. Okay, FO is the true or actual frequency being produced by the source. What's VS? V is the speed of sound. VS is the speed of the source, right? Okay, that's exactly why I reviewed it, because we see that S there and we think speed of sound. Okay, V is the speed of the waves in general, because it could be light too, right? We could be doing this with light. Vs is the speed of the source. If you recall yesterday, I said the actual formula looked like this, and VO had to do with the speed of the observer. Okay, in Physics 20 in our curriculum, we don't have to do any moving observer problems So that's out, and our formula is slightly modified. When do I use plus? When the object is approaching or retreating? Retreating, okay? Because when it's retreating, I need this bracket, okay, to be greater or smaller than 1? Smaller than 1, right? So if I have a big number divided by a bigger number, then I'm going to get a decimal. I multiply this by a decimal, f is smaller, okay? Which it should be for a retreating object. Then obviously we use subtraction for an approaching object. All right? Ringing a bell. So what we're going to work on today, we're going to do a little bit of Doppler stuff. We're also going to do a little bit of standing waves. Okay, second half of class, I'm going to review standing waves and air columns a little bit. Okay, we're going to finish that stuff up. Tomorrow we're going to do that fake quiz. Okay, that's not counting for marks. I'm just going to give you the quiz like you would have written if it was. Okay, we'll go through that and then we'll actually just correct it in class. You can have an idea of how well you know this stuff. Okay, and then that can help you prepare over the weekend for your unit exam. Okay, and I will post the review package. I think I'm scheduled to go tomorrow, so you can have a look at that over the weekend as well. Okay, so on this sheet that we were working on yesterday, okay, we didn't get very far into that as I recall. So what I would like you guys to do is kind of pick up where we left off yesterday, okay, whichever question you got to, and let's continue on with those, all right? And then there's a few on there that I'm going to want to do together as a class. Okay, I'm assuming most people probably got to 4 or 5 yesterday. If you didn't, okay, I'll blow this up a little bit so you can see it a little bit better, okay? And you can kind of pick up where you left off. Okay, if you got questions, let me know, okay, and I'll come around and help you out, okay? Do we need to do a review of the manipulation of the formula? Okay, all right, let's get to work on that, okay, and I'll just circulate and you can let me know if you need it. Yeah, just leave your phone. Remember, guys, if you did print the workbook for yourself, this is in the workbook, so you don't have to strain your eyes to read the board. Bless you. You mean for the answer?
Well, what's the starting frequency?
Oh, sorry, it's in question number 4. Yeah, sorry, I got to scroll up for that. So 305. Well, you know what, since you guys are the first person who's asked about 7, let's just do 7. Okay? All right, so on number 7 here, guys, okay, we got the train, okay, moving at a speed of 32 meters per second towards the stationary observer. So as soon as I get that, approaching, towards, okay, that key word there, then I know I can write the formula out and I can determine whether I'm adding or subtracting. Since it's moving towards, am I adding or subtracting? I'm subtracting. Okay, so now I know what formula I'm going to use. Let's get the rest of our givens. The train is moving at 32 meters per second. That would be Vs. Okay, so we got 32 meters per second. They also tell us that the whistle's frequency is 1.85 times 10 to the 3 hertz. Would that be FO or F? What do we think? Well, it didn't tell us that that's what anyone heard. It told us that was the whistle. Okay? If it's not saying you measure it, you detect it, you hear it, you perceive it, those are all the key words for F. Okay? This is just saying the whistle is. That means that's the true frequency of the whistle. Okay? So that is FO. Okay? So 1.85 times 10 to the 3 hertz. So this is one of those tricky context kind of questions where I have to read it carefully. Now, I haven't read the last sentence where it clarifies what we were just struggling with here. Okay, the last sentence says, if the speed of sound is 341, okay, so they just gave us V, what is the apparent frequency heard by the observer? Which one do you hear, FO or F? F. Okay, so we're looking for F, and we have FO. You got to read it carefully, right? It ends up being like reading comp, okay? And I've got to know what is that, what am I being given, what am I being asked to find. So the good news is we don't have to manipulate it, right? We just get to plug numbers in because it's looking for the Doppler frequency. So F will be 1,850 hertz, 1.85 times 10 to the 3, okay? Times V over V minus Vs. I should plug in the numbers because that's what I would do. And 341 divided by 341 minus 32. Okay, and I forgot to fire up my calculator, of course. But that should come out to 2.04 times 10 to the 3 meters per second. Okay, I'll punch that in here as soon as my calculator comes up. Now, brackets are important, obviously, when you punch this into your calculator. Okay? If you miss any of those brackets or do them out of order, your calculator will default to its order of operations programming, right? 341 divided by, in brackets, 341 minus 32, 2 sets of brackets. Okay? 2.04 times 10 to the 3. Okay? So the tricky thing with that one, what most people get wrong, if they get that one wrong, is they mistake one frequency for the other. Yeah. Okay, any other ones giving us trouble so far? Okay, keep going then, I'll put them back up. Okay, sorry to interrupt you here, but so for most of these questions, is there much context to them? Right? It mostly just says it's approaching or it's retreating, right? Like you don't have to think too much when you read the questions. I can't remember if it was you guys or period 4 that I was talking to this. I was telling them about sometimes like on a quiz or a test, I'll put in a question and I won't put in the word approaching or retreating. I'll put in some context where you'll have to kind of figure that out. One of the ones I gave was, you know, your car stalls on the railway tracks, okay? And you hear a train whistle of this many hertz, okay? You know, and I'll give you, you know, the speed of sound or whatever, and I'll say, what is the, you know, you're under your anxiety of being on the tracks, blah, blah, blah. What was the speed of the train? I never say whether the train is approaching or not directly, but would you be anxious if the train had already gone by? Right? Then you're not worried. You just get out and you push the car out of the way and you're not worried. You're only anxious if the train is coming at you. Okay? So sometimes you really have to read into that question to get that stuff, and I'm going to do that sometimes. I'll make a question where the context is what tells you approaching or retreating. It doesn't actually just tell you it's approaching or retreating. Okay? So be ready for that. Make sure you're reading it carefully. You're only going to get one of three kinds of questions. Solve for BS, solve for FO, solve for F. Okay? And then you could have approaching or retreating. You just have to remember add or subtract. Okay, so let's review our error column stuff here, guys. Okay, so the two kinds of error columns were open and closed. Right? I tried to and failed to demonstrate how to plumb across the top of the model, okay, which would be which kind of error column?
Closed it.
That's closed air column, right? Because the bottom is sealed, air can only go in or out through the top. Okay, that doesn't produce as wide a range of frequencies because a closed air column can only resonate at what kind of frequencies? Okay, so our fundamental frequency for a closed air column has a waveform in it that looks like this. Okay, the first antinode is 1/4 of a wavelength in the tube. Okay, the next spot that has a standing wave pattern in it would look like this. Okay, so this would be F1 and this would be F2, right? The next one that has a standing wave in it would look like this. Okay, and there would be 3/4 of a wavelength in the tube, and this would be F3. Only two of those make sound. Which one doesn't? F2. While there's a standing wave in the tube, what's at the top? What's that point called? Starts with an N. A node, right. A point of complete destructive interference. Okay, so closed air columns produce nodes at every other frequency, which means they only resonate at odd numbered frequencies. Okay, so for this one here, if the fundamental frequency was 100 hertz, the next frequency you would hear would be how many hertz? 300 hertz. Okay, remember, these numbers aren't just for fun, okay? They are the factor by which you multiply the fundamental. Okay, F3 is 3 times the fundamental. F4 is 4 times the fundamental. Okay, I guarantee you that's going to come up at some point. Okay, you have to remember that. For the open air columns, okay, at our fundamental frequency for an open air column, we have this waveform in the tube. Okay, that's F1. Do I hear a sound? I do. I got antinodes at both ends. Okay, how many wavelengths are in the tube? Half. Okay, now that is where these two formulas come into play. For closed air columns at their fundamental frequency, lambda is 4 times the length of the tube, because at its fundamental frequency, there's 1/4 of a wavelength in that tube. Okay, but for these ones, lambda equals 2L at the fundamental frequency, because only half a wavelength is in the tube. Okay, now, for an open air column, a flute is a perfect example of an open air column. Okay, you change the length of the tube by plugging different holes with your fingers. Okay, and that allows air to escape out that hole, and the distance between the opening you blow into, okay, and those open holes or that open hole, okay, that determines the length of the column of air that resonates. Okay, the shorter the column of air, the higher the pitch of the sound that you're going to produce with the flute. Okay, and all wind instruments essentially work that way. Pressing different keys opens different holes, okay, and that is going to change the resonant sound that comes out the horn. Okay, everyone with me there? All right. Next frequency for a closed air column, or sorry, for an open air column, sorry, is going to look like this. All right, that is going to be F2. How many wavelengths in the tube there? 1. Okay, because here's a quarter, here's a quarter, here's a quarter, there's a quarter. So there's 4 quarters, or 1 hole, okay, in there, 1 flow wavelength in the tube. Okay, and then at F3, okay, we should have, red. That waveform. Okay, how many wavelengths in there? 1 and a half. Okay, so the thing with the open air columns that makes them different from closed, besides the fact that they're open at both ends, is that they resonate at every harmonic frequency. 1, 2, 3, 4. Okay, they produce a broader range of sounds. That ringing a bell? Okay. Let's give a few of these ones a try here. I don't think we got them all done the other day. And what I had you working on was kind of going back and forth between the open and the closed. Did anybody finish them all? Okay, that's kind of what I thought. Okay, so let's say, 5 to 7, those are the closed, 8 and after are open. Okay, just keep working on those until we have them all done. Okay, and if any give us trouble, then we'll go through them together here. Okay, we don't have that much time because we had a shorter class today. Good morning. Yeah, sure. You can come down.